All right. So I have shared my screen. Let me know if you're able to see my screen.
Yeah. So,
Okay. So in this tutorial, we will be covering 6.2, 6.1, 2, 3, 9.1, and 9.5. So 5 exercises we will be covering. So let's get started with the 6.1. So this is on page number 416 of your text. So in the first question for this exercise is, so there are 18 mathematics major and 325 computer science major at a college. In how many ways can two representatives be picked so that one is a mathematics major and the other is a computer science major? So since the question asked is to pick one mathematics major and the other is the computer science major, so the number of ways it can be picked is 325 multiplied by 18, which is 500 and 850. Next part, in how many ways one can represent one representative be picked who is always a who is either a mathematics major or a computer science major. Okay, so here we have 325 CS majors, computer science majors, and we have 18 maths major. So we have to make sure that the representative be picked is either a mathematics major or a computer science major. So it is either one of those. So 18 maths majors. Okay. So here we will basically add them together to get the total number of ways. So 343 ways in which I can pick up one representative from different major. Okay, question? Any question? Okay, let's move on to the next one. So it's a question number 3. So part number 8. A multiple choice test contains 10 questions. There are 4 possible answers for each question. So there are 4 possible answer and there are 10 questions. In how many ways can a student answer the question on the test if the student answers every question? So if the student answers every question, then it's basically a 10 question exam which has 4 multiple choice for each question. So it's going to be, so 4 to the power of 10 is the number of ways the student can answer the questions. B part, in how many ways can a student answer the questions on the test if the student can leave answer blanks? So now, apart from the 4 possibility, we came to know that there is another possibility for leaving an answer blank as well. So this makes us basically open to 5 options to answer each question. So this will be 5 into 5 to the power of 10 is the number of ways the student can answer with an empty answer as well. Okay, let's move on to the next question. Question number 9. So question number 9 asks, how many different 3-letter initials are there that begin with an A? So, So that begins with an A. So for example, there is this letter, for example, XXX, and then this X, the first X, the first X, the first X is A. Okay, so which leaves us with AXX. Now the second X can be A to Z. Okay, likewise, so this basically leaves us with likewise, we have the third X that can also be between A to Z. Okay, um, are you able to hear me out?
Yes, we can hear you now.
Okay. All right. So here we have the first is the A, letter A, and then the second X can be anything, any number between A to Z, any alphabet between these two numbers. And then we know that there are 26 possibilities for this, and then we know that there are 26 possibilities for this as well. So the first letter is A, the second letter can be anywhere between A to Z, and the third letter can also be anywhere between A to Z. So, which basically leaves us with the possibility 1 multiplied by 26 multiplied by 26. So, which is basically 676 ways with the first letter as A. Okay, any questions? All right, no question. Let's move on to the next one then. So the next one is question number 21. It asks for how many positive integers between 50 and 100 are divisible by 7. Which integers are these? So it asks how many positive integers. So it's pretty much a straightforward question. So we will just write down the numbers which are divisible by 7 in the range 50 to 100. So 56, and then we have 63, we have 70, we have 70, we have 77, we have 84, we have 91, and then we have 98. So there are basically so seven numbers between 50 to 100, 50 to 100 divisible by 7. Okay, pretty straightforward. Part B says are divisible by 11. So we have 55, 66, 77, 88, 99. So we have basically five numbers in 50 to 100. Part C, we have are divisible by both 7 and 11. So we have to basically find a common number between them. So we see that the only common number is 77 that is divisible by both 7 and 11. So we say that 77 is the only one between 50 to 100, divisible by both 7 and 11. Okay, pretty straightforward questions. Okay, let's move on to the next one. How many strings of three decimal digits do not contain the same digit three times? So it's asking for how many strings of three decimal digit. do not contain the same digit three times. Okay, so basically we have a string. So string is just a sequence of some letters or alphabets. So in this case, we have a string of decimal. So the first decimal digit could be anywhere between 0 to 9. The second decimal could be anywhere between 0 to 9. And then the third, of course, can be anywhere between 0 to 9. This is part A. So this is like a string of three decimal digits. So 0 to 9, we have a possibility of 10 numbers for the first one, and then 10 for the second one, 10 for the third one, okay? Which leaves us to 1000. Now, we can basically we have to now make sure that it does not contain the same digit three times. So for example, 000 is one such possibility. Likewise, we have 111, 222, and then we have up till 999. So basically, we have 10 such possibilities which we want to avoid. So we basically subtract 100 minus 10, we come to 990. So 990 ways we have to represent a three decimal three decimal digit string. Okay, part B. So how many strings of three decimal digit begins with an odd number? So as we already know that total possibility is 1000, coming from this line here, that begins with both odd and even for a three digit string. Since we need the possibility for only the odd digit, we will basically divide by 2. So we have 1000 divided by 2, which is equals to 500 of 500. So 100, for example, starts with odd, 200 starts with even, and likewise we have that streak. Okay, so basically we have 1000 possibilities that start with both even and odd. Therefore, for only odd, we have 500 ways. All right, any questions so far? All right, sounds good. Let's move on to exercise 6.2. So for exercise 6.2, it's available on page 426 of your textbook. Uh, so let's take the first question. So we have to show that in any set of 6 classes, each meeting regularly once a week on a particular day of the week, there must be 2 that meet on the same day, assuming that no classes are held on weekends. So we have to basically show that in any set of 6 classes, each meeting regularly once a week on a particular day of the week, there must be 2 that meet on the same day, assuming that no classes are held on weekends. Okay. So we have the assumption there are no classes on weekends. Now, because there are 6 classes in 1 week, we get 5 classes. Now here we use the principle of pigeonhole principle to show that at least 2 classes must be held on the same day, right? Because there are 6 classes, but because the classes are held only 5 times in a week, so there must be one class which basically occurs or happens with the other class. So this is the principle which is actually known by the name of pigeonhole. So we apply that here. Next question. Show that among any group of 5 not necessarily consecutive integers, there are 2 with the same remainder when divided by 4. Okay, so we have to show that among any group of 5 not necessarily consecutive integers, there are 2 with the same remainder when divided by 4. Okay, so let's take the number 4. Okay, so we take 4, we start with the number 4, and then we divide it by 4, which gives us the remainder 0. We take 5 divided by 4, which gives us remainder 1. We have 6, we divide by 4, which gives us remainder 2. We have 7, we divide by 4, we get the remainder 3. We have the next consecutive will be 8, so we divide by 4, we get remainder 0. So because there are 4 possible remainders when an integer is divided by 4, that is the possible remainders are 0, 1, 2, 1, 2, 3. Now we use the pigeonhole principle again. Using the pigeonhole principle, it implies that given fixed integers, at least to given 5 integers, at least 2 have the same remainder. Okay, so just like so we take 5 integers starting from 4, 5, 6, 7, 8, 5 consecutive ones. So there are 2 among the 5 consecutive integers which have the same remainder. So we basically proved it using the pigeonhole principle. Questions? All right, let's move on to the next one. Okay, question number 9. So let n be a positive integer. Show that in any set of n consecutive integers, there is exactly one divisible. Okay, all right. So let n be a positive integer. Show that in any set of n consecutive integers, there is exactly one divisible by n. Right. So for example, let's take a plus 1, a plus 2, a plus 2, and then let's say if the string goes on, and then we have until n minus 1. So these are the consecutive numbers, so be the integer in the sequence. Okay, now the integers uh, a plus I mod n, a plus I mod n, I equals, so what we are doing is we add a and then we add I, some integer I, we divide, basically we divide it with n, and then we take the remainder. So I, the number I is either 0, 1, 2, 3, so on up to n minus 1, and we know that they are distinct. Now because 0 is less than a plus j minus a plus k is less than n whenever 0 is less than or equals to k is less than or equals to j is less than or equals to n minus 1, because there are n possible values for a plus 1, a plus I mod n, and there are n different integers in the set. Each of these values is taken on exactly once. It follows that there is exactly one integer in the sequence that is divisible by n. Some number x and some number y. If y is a multiple of x, then the mod of x divided by y would be 0. Okay? So if so for example, if we have two numbers x and y, and x, for example, is a multiple of y, or y is a multiple of x, then if we divide them with each other, the remainder is going to be 0. Okay, so what we did is we basically we basically went from a to a plus n minus 1, just one number less than n. So because we have to show up to n, right? So show that in any set of n consecutive integers, so these are the set of n consecutive integers, there is exactly one divisible by n. We have to show that. So this is the sequence we are assuming, and then we say that, okay, so if we take a plus I, so I, for example, can be anyone from 0 to n minus 1. If we add it to a and divide by n, we get distinct remainders according to this, right? Now, because there are n possible ways for a plus I mod n, and there are n different integers in the set. Therefore, each of these values is taken on exactly once. So therefore, we can say that there is exactly one integer in the sequence that is divisible by n. Okay, let's move on to the next one. So we have to show that if 5 integers are selected from the first 8 positive integers, there must be a pair of these integers with a sum equal to 9. Okay, so basically what we have to do is we have to group the first 8 positive integers into 4 subsets of 2 integers each. Okay, so we group the first eight 8 positive integers into 4 subsets of 2 integers each, so that the integer of each subset add up to 9. So we will take subsets like we have one subset, it's 1 to 8, and then another one could be 2 to 7, and then the other one will be, let's say, 3 to 6, and then the other one will be 4 to 5. Okay, so if 5 integers are selected from the first 8 positive integers, we use a pigeonhole by the integers by the pigeonhole principle. At least 2 of them come from the same subset, right? Because there are um, 8 positive, there are 5 integers selected from the first 8, right? And then we already know all the subsets, which adds up to 9, right? So if we have we have to pick 5 from the 4, we know that there is at least 2 that comes from the same subset. Okay? Therefore, we can say, therefore, there is a pair summing up to 9. All right. Any questions? Okay, no question. Let's move on to question number 25. So we have to show that whenever 25 girls and 25 boys are seated around a circular table, there's always a person, both of whose neighbors are boys. Okay, so we can basically uh, prove this. So let's start. Number. So we have here. We have here. So number. So we what we will do is we basically number the seats. So number the seats around the table from 1 to 50, because there are 25 boys and 25 girls. So each chair will get a number between 1 to 50. Since the total number is 50. Okay? And think of seat 50 as being adjacent to number 1. So basically in a circular way, basically in a circular way. Okay. Now there are 25 seats with odd numbers and 25 seats with even numbers, right? Because they're from 1 to 50, 25 is odd, 25 is even. So if no more than 12 boys occupied the odd numbered seats, then at least 13 boys would occupy the even number seats, right? So if 12 boys occupy the even number, 12 boys occupy the odd number, then there will be 13 boys that occupy the even number seats. Okay, and then we can do the vice versa as well. So if, for example, 13 boys occupy the odd number, then there will be 12 boys who will occupy the even number. Okay, so and vice versa. So without loss of generality, assume that at least 13 boys would occupy the 25 odd number seats. Okay, then at least two of those boys must be in consecutive odd numbered seats numbered seats and the person sitting between them will have voice as both of his or her neighbors. Okay, so basically what we did is we have for 25 boys and 25 girls, and then they're all sitting in a circular way. We numbered the seats between 1 to 50, and then we assume that there are 13 boys that are occupying the odd number seats. So that leaves us with an assumption that the number 1 and 50, because they're adjacent to each other, so we can conclude that at least two of those boys must be in consecutive odd number seats, and the person sitting between them will have voice as both of his or her neighbor. Okay, let's move on to the next exercise. So exercise 6.3, this is on page number 435 of your textbook. Question number one. So we have to, this exercise is about permutation. So in permutation, we have to list all the permutation of the set A, B, C. So, so we would take A, B, C, it's called A. A, B, C, this next one could be A, C, D, the next one will be B, A, C, uh, next one B, C, A, C, A, B, and we have C, B, A is the list of all the permutations of that set. Okay, next one. We have to find the value of each of these quantities. So we have the permutation, and then it's in the range 6 to 3. I'm just writing down the formula. P for a number a to b equals to a factorial divided by b minus a factorial. Okay. So if we have to take a permutation of a and b, it's according to this formula. Okay. So let's take part A. We have a p. Here a is 6 and b is 3. So we take 6 factorial, which is equals to 6.5.4, which is equals to 720. And then we have 3 factorial, which is equals to 3 to 1, which is equals to 6. If we divide 6 factorial with the 6 factorial divided by 3 factorial, this is going to be 120. Okay, so we take the a factorial. A in our case is 720, and then we have this b minus a. B minus a will be, so 6 minus 3 will be 3. So we take the factorial of 3, which is 6, and then we take 720, we divide it by 6, just plugging in the values for these b and a. Okay. Let's do one other part here. So isn't, somebody is asking, isn't it minus 3? Minus 3, why? Right. So even if we take the factorial of minus 3, right? So it's always going, so b minus 6, 3 minus 6 minus 3, but we take the factorial, right? So it's always coming as positive. Okay. So 3 to 1. Okay. All right. So let's take just another one. This is just simply plugging in the value. So we have P88. So this is an interesting one. So we know that the 8 factorial is basically um, so we have this 8 factorial. According to this equation, so we have 8 factorial divide by b minus a is 0, right? 0 factorial, right? So if we have 8, this factorial, 8 factorial divided by 0 factorial is, so by the way, 0 factorial is not 0, it's 1. So this is something that we should keep in mind. So 8 factorial divided by 1. So the answer will be 8 factorial itself, right? So if we take 8.7.6.5 and dot 3.3.2.1, and then this will come to around 40,320. Okay, so this was the answer to this. Let's just do one more just to get a hang of it. So we have P10.9. What we do is just like before, 10 factorial. 10 factorial, we have divide by 10 minus 9 is 1 factorial. So it is going to be 10 divided by 10 factorial divided by 1 factorial is 1. So this is 10 factorial itself. And then 10 factorial equals to 10.9.8.7.6. And then we have 1. Okay. So, and then we can do the calculation to get in some answer here. So pretty straightforward questions, no big logic, just the plugging in the values into the equation and getting the result. Any questions here? right, sounds good. Okay, let's move on to the next one. We have a group of containing contains n men and n women. How many ways are there to arrange these people in a row if the men and women alternate? So let's um, so here we will say that because there are two possibilities, right? Two possibilities because there are men and women, right? And then there are n men and n women. So we take n factorial, two, right? Ways to arrange men and women to arrange men and women in an alternate way. Okay? So let's consider a group of four people. So let's say we have a group of four people. So with the two men and two women, right? So according to the equation we have, so 2 n factorial is the total number of people. So we have um, n factorial, so two men and two women, so 2 factorial to the power of 2. So this is going to be 2 to 2 to the power of 2 will be 4. So this is going to be 8, right? So there are 8 ways in which we can arrange. So for example, what could be those 8 ways? So for example, let's say if we have the first man followed by another woman, then the man two followed by the other woman. So this is one way. The other way will be man one followed by the woman two, and then we have the man two followed by the woman one. Okay, and then we have men 2 followed by woman 1. We have m1 followed by woman second. We have men 2, woman 2. We have first men, and then we have the second first woman. Likewise, we can say we have woman 1, m1, woman 2, m2. Okay, so woman 1, m2, woman 2, then M1, and then we have woman 2, men 2, woman 1, and then men 1. Lastly, we will have woman 2, men 1, and then we have woman 1, and then men 2. Okay? So likewise, we can see that there are 8 ways. If we plug into this equation, we can definitely figure out that the sequence for alternating setting of men and women. All right, so let's take a quick break here, and I will catch up with you guys in 5 minutes. So if you guys want to grab some water, so you can go ahead and do it. All right, let's continue. Hmm. Any question for um, this question number 13? Okay, no questions. All right, let's move on to the next one. Okay, so question number 19. So we have a coin that is flipped 10 times where each flip comes up either head or tails, how many possible outcomes are there in total? So we have flipping coin. So if we flip a coin once, then there are two possibilities. So it can either land on a head or a tail, right? Possibilities. Two possibility. If we flip coin two times, then we have 2 to the power of 2, which is four possibilities. Four possibilities. If we flip coins 10 times, so flipping coins 10 times, 10 times, so we have 2 to the power of 10, which is 124, 1024 possibility. Okay, 1024 possibility. Okay, pretty straightforward. So if we flip a coin once, it can either land on head or tails. If we do it twice, it can land for the first time, it can land on head or tail, then second time as well can land on head and tail. Flipping each time, it can only basically comes to either a head or a tail. So there are just two possibilities. So if we flip it 10 times, there are 1024 possibilities. Okay, pretty straightforward question. Next one, let's take, so find a formula for the number of circular R permutations of n people. So so there are basically the circular permutation. We have to find the formula for that of n people. So this is just a formula that so basically the formula for the number of circular R permutation of n people is basically we have n factorial, we divide it with r, and then we have n minus r factorial. Okay, so it's just a formula that we basically have to list here. So pretty straightforward, no logic here. Right, any question from 6.1, 6.2, or 6.3 so far we have covered? All right, no questions. Let's move on to the exercise number 9.1 then. So 9.1, it's on page number 608. So in this exercise, we take the first question and then we have to list the ordered pairs in the relation R from A to B, where A, B belongs to real numbers if and only if A equals to B. Now, if A equals to B, then we have to list down the ordered pairs. So let's take the part A. So we will have this set, and then the first pair will belong to the first pair because it's A equals to B, so we take 0 and then we take 0 from here, which is 0 0. We have 1 from A and then we take 1 from B. Likewise we do 2 2, and then we do 3 3. Okay, we won't be doing 4 4 because B does not have 4. Let's take part C. So C, A is greater than B. So for this one, we have quite some options. So we take 1 and then we take B 0. Okay. And then we take 2 and then we take 0. We take 3, we take 0 from B. We take 4 from A and 0 from B. 4 from A and 0 from B. So 4 is greater than 0. Okay. So now we have 3. So we have A is greater than B. So we have 1 0 2 0. All right. Okay. So 1 0 2 0, and then we have here not this one because A is greater than B. Here we take 1 0 2 0. We have 2 1, and then we have 3 1. Sorry, 3 0, and then we have 3 1, and then we have 3 2, and then we have 4 0, and then we have 4 1, and then we have 4 2, then we have 4 3. Okay, so basically we take 1 1 0 2 0 2 1 3 0 3 1 3 2 4 0 4 1 4 2, and then we have 4 3. Okay, when A is greater than B. Okay, we couldn't go for example 0 0 1, because in that case A will be less than B, so we don't want that. Okay, let's do another part E. So in part E we have to take GCD, where GCD of AB equals 1. Okay, so what we have to do is we have to take the greatest common divisor. Okay, so greatest common divisor we have here. So we take 0 1, 1 0, then we have 1 1, then we have 1 1, and then we have 1 2, greatest common divisor for which equals to 1. The next one will be 1 3. After that 2 1, have 2 3, 3 1, 3 2, 4 1, 4 3. Okay, so 0 1 1 0 1 1 1 2 1 3 2 1 2 3 3 1 3 2 4 1 and 4 3. So for this set here we have all pairs for which GCD AB, so this pair equals to 1. Okay, so basically just we follow what the question asks for, no fancy logic. So somebody is asking that for part E and F, it represents a statement as true. The equals to 1 represents statement as true. It represents that the GCD for this pair, like 0 1, for example, it has to equals to 1. So for example, so for this one here, the LCM, it has to equals to 2 for all the pairs that we list here. So it has to hold, that is, it has to be true, so that this is equals to 1. If this is true for that pair, then it's going in this set. Okay, all right, let's move on to the next one then. So this question number 5 here, determine whether the relation on the set of all web pages is reflexive, symmetric, anti-symmetric, and or transitive, where AB belongs to RF and only if everyone who visited web. So here we will just have to write down the it's either reflexive relation or symmetric or anti-symmetric or transitive relation. So I'm just going to write down for you guys. So but you are supposed to know what is basically reflexive, transitive, or symmetric or anti-symmetric. Okay, so for example, for the first one, we have everyone who has visited web page A has also visited web page B. So if you know the definition of these reflexive, symmetric, anti-symmetric, and transitive, then you can basically make a very good guess that okay, so it's referring to this relation here. So for example, for this one, this is reflexive. Okay, so part B, there are no common links found on both web page A and web page B. So because there are no common links that are found, there is no relation in terms of finding the link on both web page A and web page B, we can say that this is a symmetric. So, as part C, there is at least one common link on web page A and web page B. So there is at least one common link. When we have at least one common link, so because this is also a property for a symmetric relation, so this will comes as symmetric. There is a web page that includes links to both web page and web page B, just like above. So this also represents symmetric relation. Okay, next question. So give an example of an irreflexive relation on the set of all peoples. So we have the set of all peoples, and then we have to give an example of an irreflexive relation on them. So irreflexive relation, there can be a couple of examples. For example, there can be a pair AB that belongs to the relation if and only if A is, for example, taller than B, then this will be a irreflexive relation. So, for example, we have AB pair, AB pair, and then we have AB pair. Why is coming bolded? Okay, AB pair, and it belongs to R if and only if A is taller than B. So basically just have to know the definitions for these terms. So it is irreflexive, and then you should be able to answer those questions pretty easily. So no fancy logic here, just understanding the meaning of the terms. Okay, let's take on the next 9.5, which is on page number 646 of your textbook. So in this exercise, we will also be dealing with the relations. So in here, we also have to know the definitions of relations, different relations. We have like equivalence relation, like reflexive, non-transitive, and symmetric relations. So if we know these definitions, we are able to answer the questions pretty easily. So we can get past that if we don't know the definitions. So question number one, we have which of these relations on 0, 1, 2, 3 are equivalence relations? Determine the properties of an equivalence relation that the others lack. Okay. So we have to basically determine which set is which kind of relation. So part A. So we have this 0, 0, 1, 1, 2, 2, 3, 3, because here we see sort of equivalency. So we can right away tell that this is an equivalence relation. Okay, let's take part number C. So part number C, we have 0, 0, 1, 1. We have 1, 2, but we also have 2, 1. We have 2, 2, and 3, 3, right? So here we also have the equivalence relation. Okay, So just basically knowing the definition. Let's move on to the next one here. So we have to define three equivalence relations on the set of buildings on a college campus. Determine the equivalence classes uh, for each of these equivalence relations. So here we have to define three equivalence relationships. Okay, so there are many possible answers for this one. So for example, for one equivalence relationship can be, for example, two buildings are equivalent if they are opened during the same year. An equivalence class consists of the set of buildings an equivalence class consists of the set of buildings opened in a given year, uh, as long as there was at least one building open that year. So as long as there was at least one building opened that year. Okay, so this is one equivalence relation where we have, for example, the two buildings, they open during the same year. Okay, so there are many different possibilities. This was one of them. The second one could be two buildings are equivalent if they have the same number of stories or the floors. If they have the same number of stories, the equivalence classes are the set of one-story building. The equivalence classes are the set of, for example, if we have one-story building, so equivalence class will be a set of one-story building. Story building, the set of two-story buildings, and so on, right? So sort of relationship that we see here, right? Part is 0 0. So for example, we have one floor, so we have different classes belonging to that equivalence relation, and so on. So one class for each n for which there is for which there is at least one n-story building. Okay, so likewise, we can also have another possibility. So you guys can basically reflect on that. So just to give you an idea, so there are a couple of possible answers for this question. Okay, move on to the next question. So question number 11. So show that the relation R consisting of all pairs x, y such that x and y are bit strings of length 3 or more that agree in their first 3 bits in an equivalence relation on the set of all bits on set of all bit strings of length 3 or more. So it's basically the question on the strings again, like we did before. So what we will do is we will assume that there is a bit string of length 3 or more, and then we will take that assumption into, we will prove this question taking that assumption. So let x be a string of length 3 or more. Okay, now because x agrees with itself in the first 3 bits we have XX that belongs to R. Okay, belongs to relation. So hence, because it has a first three bits which agree with itself, so therefore we say that this is a reflexive relation. So hence R is reflexive. Okay? Now suppose that we have pair XY belonging to that relation, that X and Y agrees in the first three bit. X and Y agrees in the first three bits. Okay. Hence Y and X agrees in the first three bits as well. Hence Y and X agrees in the first three bits. Thus YX also belongs to R. Thus this pair YX belongs to R. Okay. Now if this pair XY and YX are in this relation, then X and Y agree in the first three bits. Then X and Y agrees in the first three bits. Hence we can say three bits, not parts. Hence we can say this pair X Y XY, this belongs to R. It follows that R is transitive. Okay, so basically what we did is we assumed that X be a string of length 3 or more, and then we say that X agrees with itself in the first three bits, so therefore XX belongs to the relation. And because it's a pair of the same numbers, so therefore we say that it's a reflexive relation. And then we suppose that there is another pair XY which also belongs to R, and we make some assumptions, and then we prove that YX also belongs to R. Now if both of them belongs to that relation, then X and Y agrees in the first three bit, therefore its R is a transitive relation. Any questions so far? Any questions from any previous exercise that we did today? All right, sounds good. If there are no more questions, that is pretty much everything for this tutorial, and I'll see you guys in the next tutorial. So take care, guys, and good luck with your test that you have done. Okay, all right, thank you. Take care.